Here at 2 o'clock on the East Coast, we have Luke Schoenwetter from the FreeFlyer development team to tell us all about FreeFlyer optimal control. And he's going to be specifically walking through an example for continuous thrust GTO to GEO. So Luke, if you can come up on stage and share slides, and we can get going.
All righty. Can you hear me, Michael?
Yes, I can.
All right. And screen check.
Slides look good. You're good to go.
Awesome. Well, hello, everybody, and welcome. I'll be discussing the new FreeFlyer optimal control features, specifically how they can be used to design a transfer from geostationary transfer orbit to GEO. First thing I'd like to point out is that the scenario I'll be walking through today is actually a FreeFlyer sample mission plan. I did make a couple modifications in order to get the output you'll see in the slides, but overall, the whole thing remains pretty much the same as what you get in your FreeFlyer download. And if you have FreeFlyer 7.8 downloaded, you can find that mission plan that we're looking at today at the path down in the bottom right. It's in your documents folder. If you'd like, you can even open up for reference and follow along, although that's certainly not required. So let's jump right into the scenario that we'll be looking at. So we're going from we're designing a transfer from GTO to GEO. So we're going to start out in low Earth orbit, which in this slide is the red circle tied around the Earth. We're going to model an impulsive delta V that's going to be simulating the booster that's going to put us into GTO, which is that yellow elliptical orbit coming off of the red LEO orbit. And then from there, we move into the continuous thrust transfer, which is the orange piece of the trajectory. And finally, we end up in that green GEO orbit. Now, these little white lines that you see popping off of the transfer phase, that's the thrust direction and the thrust magnitude. That's what those lines, the information that those are encoding. So at each point along the trajectory, those lines are telling you where you need to point your thruster, or rather the force that your thruster is creating in order to fly the trajectory. Here's a side-on view of that same thing we were just looking at. You can see we're launching into LEO at an inclination of about 30 degrees or so. So we'll need to get rid of that on our way out to GEO. So how do we take this scenario and turn it into an optimization problem that FreeFlyer can understand and solve? So we start out again in LEO, and we're going to create 3 phases where we were using that TrajectoryPhase object that Nate was just talking about a few talks ago. And we're going to use 3 of those TrajectoryPhase objects to solve this problem. The first one is going to model the parking orbit. The next one is going to model that post-boost phase, the GTO orbit. And then the last one will model the continuous thrust transfer. And we don't really need a TrajectoryPhase object to model that final GEO orbit, just because we can apply the constraints that we need to apply directly to the tail end of the transfer phase in order to make sure that we've achieved geostationary orbit. Now the post-boost phase and the transfer phase are pretty easy to see in this picture, but the parking orbit's kind of hard to see. Here's a zoomed in view of that. You can see it's really short compared to the other 2. And that's just because we don't need to model a lot of the LEO orbit in the actual problem the numerical problem that is. That will decrease the size of the problem that we need to solve, while still giving us a point to apply the constraints that we need to apply in order to make sure that we're actually starting from that LEO orbit. Now, as far as the TrajectoryPhase object goes, I will do a quick little introduction / extension of what Nate was talking about earlier when he introduced these new features. So the TrajectoryPhase is basically a discretized version of a trajectory segment. So if you think about, your path through space, at each moment in time, you have a position and a velocity. These trajectory phase objects hold that information at a discretized interval. And those pieces, or the things that make up the discretization, are called nodes. And so those nodes are visualized in this frame as those little dots along the trajectory. And what this allows us to do is decrease some of the problem sensitivity, as opposed to solving the problem via integration. We can now use these nodes to solve using collocation. Some of the other things that these trajectory phase objects do is allow us to easily do things like link two phases together. Say you have an Earth phase and a Mars phase, like in Nate's talk earlier. You can link those up really easily. It also provides convenient ways to add boundary constraints to the problem, provides easy access to those endpoints. And again, using the collocation and this discretized node structure to solve the problem results in very, very sparse problems, which allows the sensitivity of the problem to be decreased. It's kind of akin to using a giant multiple shooting structure to solve a problem, and how that lowers the problem sensitivity. So let's generate an initial guess, add some constraints, and solve the problem. So here's our LEO orbit and our GEO orbit. Again, our the initial and final conditions. And you can see that aqua colored trajectory phase object there connected to the LEO orbit. We're going to use the add nodes feature, or the add nodes method on the trajectory phase object to generate the initial guess for that phase. We're going to set up our spacecraft such that the parameters are the same as that LEO orbit. And then what this method is going to do is it's going to propagate the spacecraft for a certain amount of time, in this case, 0.05 hours. And it's going to save off 5 of those discretized nodes during that propagation to create the initial guess for that phase. And we use the lock method to lock the variables for the first node of that parking orbit phase that we just created. And that's just going to ensure that we stay connected to that LEO orbit while we're solving the problem. Then we're going to use that add nodes method again. I'm not going to put it up on the screen for each one of these phases, but really we're using that to generate the initial guess for each phase. So we'll propagate the spacecraft again, save off some of those nodes. And now we have this guess for the GTO orbit. And we'll use a delta V link constraint in between the parking orbit phase and the post-boost phase in order to connect those. So we want it to be connected in position to the parking phase, but we're going to allow some sort of delta V to model the booster that's putting us into GTO there. Next, we're going to propagate and save off nodes for the transfer phase. And we could do some fancy things here, generate an initial guess that maybe looks closer to the solution. But we're not going to do that. We're just going to provide a ballistic initial guess. So we'll provide a couple of revolutions and not give any sort of control structure for the initial guess. And we'll just go with that for now. So we want to set the control type for the transfer phase to 1, which is the simple thruster control model. And we want to add a phase link in between that post-boost phase that we just generated and the transfer phase to make sure that those link up. And then at the end of the transfer phase, so at the last node, we're going to add a radius constraint so that that's just to ensure that we're hitting geostationary radius at the end of the transfer. And we could add similar constraints for inclination and eccentricity. But instead, we're going to do something a little funny and throw those things into the objective, create a pseudo Lagrangian objective of sorts. And that's just going to tell the optimizer that, hey, we want to drive these things towards 0, which is, of course, what we're really looking to do when we're getting into geostationary orbit. We want 0 inclination, 0 eccentricity. And then also in the objective, you can see that the delta V for that transfer phase, we want to minimize the propellant usage that we're inducing while we're making our way out to GEO. So that's the concept of the problem. Now we get to everybody's favorite part, which is looking at code. So let's walk through this real quick. Like I said, we want to set up our spacecraft so that we are in that LEO orbit. So these are those parameters there, and we'll set our initial mass. You can see these 3 trajectory phase objects come up next. So we instantiate those, and then we're setting up that control model for the transfer phase. So we set the control type, tell it what we want the thrust and the ISP to be. And now we're going to add nodes for the parking orbit phase, generate that initial guess, add nodes for the post-boost phase. And this resample nodes method that you see being used here, that is basically just going to take the nodes that we've added to the phase and restructure them to make the problem a little more tractable for the optimizer. And then we'll do the same thing for the transfer phase, propagate, save off nodes, and resample those nodes. So here in this script, and by the way, this isn't all of the script necessary to recreate the things you're seeing here. There's more script that I'm not showing. Again, you can see all of the code that goes into this if you go to the FreeFlyer sample mission plans in 7.8. And that path to the mission plan, I'll put up on the screen again at the end of the presentation in case you didn't catch it the first time. So no worries. But so in this portion of the script, we're going to be setting all of the constraints on the trajectory phase objects to model the physical constraints that go along with the scenario that we're trying to solve. So we want to lock all of the variables at the first node of the parking orbit phase to make sure that we stay attached to our initial LEO orbit. And we're going to lock the time of flight of the parking orbit phase and the post-boost phase. This isn't something that is strictly necessary, but it'll make the problem a little easier for the optimizer to solve. Like I was saying earlier, the parking orbit phase, we don't need to model a large portion of that orbit. We just need a tiny little bit of it to apply constraints to. So we want to keep that time of flight really low for the parking orbit phase. Therefore, we're going to lock the time of flight so that it can't be moved around by the optimizer. And for the post-boost phase, we already know that we want the transfer phase to start out near apoapsis, which it does in the initial guess. So we can be reasonably certain that if we lock the time of flight for the post-boost phase, we're going to end up with the transfer phase starting at apoapsis, regardless of what the optimizer does, as long as we lock that time of flight. So we'll do that too. These two constraints that you see here are kind of like guiding hands. These don't have anything to do with the actual problem scenario that we're trying to solve, but by setting mass bounds with that, so we're basically saying that we want to set mass bounds for the entire path of the transfer phase. So as the spacecraft is throwing mass out the back, the mass is decreasing, but we never want the mass to decrease below 20, or rather, we already know that the mass should never decrease below 20. So we set that bound as a guardrail for the optimizer. And same thing for this radius path constraint. We already know that there's a limit to what the radius should be along the entire trajectory. You know, the optimizer doesn't need to worry about trying a radius of 1 e to 10 to the 8th power. That's too much radius. So this is another guiding hand to the optimizer, guardrail to keep it from trying things that are just totally unnecessary. And this last radius constraint, we're going to apply this to the last node of the transfer phase. So the first radius constraint, we applied that along the entire path, so to every node in the transfer phase. This radius constraint we're going to apply only to the last node, and this is going to be our geostationary radius constraint, 42164. Next, we're going to add all of those trajectory phase objects to the optimizer. And what this does, what's happening in the background here is the optimizer is looking at all of the nodes that are attached to these trajectory phases, all of the constraints that we added just above, and it's assembling all of those things into one big optimization problem for us. Now we're doing all of those links between the parking orbit phase and the post-boost phase. We're using that delta V link constraint to model the impulsive booster delta V. And we're also linking all of the other variables without any delta in them. So that's position, mass, and epic. And then we'll just link the post-boost phase and the transfer phase straight up, since there's no impulsive delta V there. So this add phase link is essentially equivalent to what we did right here, except for the delta V constraint. We're also here, we're also linking the velocity straight up, so no delta V. And now we've created the problem. Here's our initial guess for those three phases. You don't see the LEO orbit and the GEO orbit modeled in here, but we can hit run on the optimizer. And what you're seeing is a visualization of what's happening in this little script loop up in the right. This is called the evaluation loop for the optimizer. So it's, it's moving the thrust vectors around, and it solved the problem. So this is what the solution looks like, or at least the solution that we found, given our problem setup. This is what it looks like with the LEO orbit and the GEO orbit thrown in there. And one interesting facet we can look at is the control structure. You can see there are places where the control norm on the top there kind of spikes up. There are places where it's lower. A control norm of 1 is basically max thrust. Control norm of 0 is no thrust. So, and you can see the places where we're using more thrust, our spacecraft mass decreases more quickly than when we're using less thrust. So an interesting next step that isn't in this sample mission plan, but if you were to take this analysis a step further, you could potentially create new trajectory phases for the transfer phase where you essentially zero out the thrust for these places where we already know the thrust is near 0. And yeah, again, there's that the path for this sample mission plan. If you'd like to go check it out. We have an assortment of other optimal control sample mission plans that are in FreeFlyer 7.8 that you can also take a look at. And with that, I'll open it up for questions.
All right, thanks very much, Luke.
Mm-hmm.
Let me just get some questions up for you. If you have any questions for Luke or for any of our speakers, feel free to use the Q&A feature in Zoom to get those questions to us. So Luke, thanks for telling us all about optimal control. Question 1, what advantages does collocation offer rather than like general optimization with numeric integration?
So the main advantages for collocation over integration are less sensitivity. So with integration, you have a large variance from your initial state to the end of your propagation. Collocation gets rid of that, so it can help the optimizer explore the state space for the problem without getting into bad states. And it also can be a lot faster in a lot of cases.
Awesome. How accurate does your initial guess need to be for an optimal control problem like you've shown?
Well, again, this goes kind of hand in hand with what we were just talking about with the sensitivity. For this problem, we were able to give the optimizer an initial guess that looked absolutely nothing like the solution. We were a completely ballistic initial guess, no control for the guess in this problem. And we were able to generate the solution. And that's due to, again, the collocation and the decreased sensitivity that you have when compared with integration.
Gotcha. Well, you sure make it sound easy. You've shown a couple sample mission plans And we saw kind of step-by-step instructions from Nate earlier. Besides going back and seeing that recording, what are other ways that I can set up my own optimal control problem?
Yeah, so the sample mission plans are a great start. There are lots of things in there for you to copy and paste if you so choose, or you can use those mission plans as a jumping off point, just modify them slightly in order to do something a little bit different. There's also an optimal control guide in the help file that you can check out. If you open up the FreeFlyer help file, I believe in FreeFlyer, it's, there's up in the very top tab, there's a help, and you scroll down in that menu and hit open help file. And there's a search function in there. You can search for the optimal control guide. And there's a whole page describing in detail how to set up an optimal control problem.
Awesome. Do you have a recommendation for which optimizer to use? We have several in FreeFlyer that best works with these optimal control features.
Yeah, so IPOpt is the default. If you don't have access to SNOpt, then IPOpt is definitely the one you want to use. We have three. There's IPOpt, NLOpt, and SNOpt. SNOpt doesn't come with FreeFlyer out of the box because there are licensing things that we can't get around there. So you have to have your own SNOpt license and bring your own SNOpt library in order for FreeFlyer to use it. SNOpt works great for optimal control though, as does IPOpt. NLOpt, on the other hand, doesn't support sparse matrix manipulations, so it doesn't work well, or it doesn't play nicely with the collocation features that are in the back end of the trajectory phase objects. So more than likely, if you try solving a problem that has trajectory phase objects in it using NLOpt, it won't go very well.
Gotcha. A question from Jessica. She asks, how would this look with the trajectory to lunar orbit?
Well, you could certainly try it out and let us know. We would love to see what sort of results you get. Unfortunately, we don't have an SMP that does that, so I couldn't say off the top of my head what that sort of transfer might look like. But I can say with confidence that you can use these sort of features to design that sort of transfer. You would just need to modify, say, the initial guess that you're generating and the sorts of constraints that you're applying at the end of the problem. Here we're applying constraints that say we want to be in geostationary orbit. In the Earth to Mars mission plan that Nate was looking at earlier, at the end of the mission plan, we're connecting to Mars. Same sort of idea. We just need to make those constraints such that we're connecting to some sort of lunar orbit.
Yeah, absolutely. And we have a couple of different sample mission plans that do Earth to Moon or Earth to Mars, without this optimal control. And then you could add that in, or we have some interplanetary optimal control in SMP's format that you could use and then translate that to the lunar problem. Also, Jessica, stay tuned. We'll be talking about cislunar trajectories for a good portion of the afternoon today. Another question, is it possible to set constraints on the maneuver thruster, such as the lowest percentage of thrust that the engine can provide?
Yes, there is, I don't have an easy way to pull it up right now, but there is a property that lives on the simple thruster options object. And that is, so referencing it from the trajectory phase object, you need to go to trajectory phase dot control model, and then from there to dot simple thruster options. And on that object, there is a norm bounds property, I believe is what it's called. It has norm in the name. So if you use the search function in the help file, I'm sure you'll be able to find it. But that property is an array and it holds two values. by default, there's 0 and 1. And what those two values are saying is that the lower bound for all the thrust vectors is 0 and the upper bound is 1. So say I wanted to constrain the norm to be 1 along the entire trajectory. In other words, I want to use max thrust along the entire phase. I would set the lower bound to 1 and the upper bound to 1. And obviously you can configure those values however you want. So you could configure whatever sort of thrust percentage you would like.
Awesome. I think that answers it. And we will try to also respond to this question so that you have some of that typed out. I think that is all the questions. Oh, one more. Can you change the colors of the control vectors drawn on these visualizations?
Yes, you can. You can change them to an arbitrary constant color. So I could change them all to blue if I wanted them to be blue, or whatever color you want. There's also color modes that you can choose from. So just like Nate was talking about in his talk, how you can color the path of the trajectory phase to show you where there is error in the trajectory. So places where there's error will show up as red. Places where there's dynamical integrity will show up as green. You can do that sort of thing for the control vectors too, in addition to being able to set a constant color for all of them.
Awesome. Well, thank you very much, Luke, for a great talk on optimal control. We're going to take just a few minutes break, and at 2:30 we'll have Clark Newman sharing on estimating drag coefficients from TLEs for reentry predictions. So we hope you'll join us in just a few minutes.